This is a quantum mechanical angular momentum operators, and we are going to prove some certain elements here that are very crucial and important in our computations in quantum mechanics. So pay attention, as all details are important, as they form a prerequisite point for us to be able to do computation later on. So we might be needing some things here that are very important. So let's get started. Let's take a different color. In this case, we want to look at angular momentum operator. So classical angular momentum is a vector quantity that is denoted by L, and this L is a vector which we can denote it L. It is equal to R cross P. R cross P. All of them are simply vector quantities, so it is R cap. So now it is a cross product. You can watch my mathematics videos on cross and dot product so that you can know how to do these common multiplications. So therefore, if R is cross P, this means that L is going to be given as I. We have JK, I, J, and K. We are going to cross this with X, Y, Z, X, Y, Z, and then we have our PX, PX, PY, PZ, PX, PY, and then PZ. If we do our cross product here, we will simply have YPL. This is YPZ. YPZ minus ZPY minus ZPY. You simply close this I side and take the cross product of JK. This will give you YPZ minus ZPY minus ZPY. Multiply this is the I part of it, and then we do the same. So this is the resultant. This is what we are going to have, the resultant vector of our cross product. And when we do that, we will simply have, this is going to be equal to LXI minus LYJ minus LYJ plus LZK plus LZK. So this is what you will get here. So let's focus on one component of angular momentum and let's say that we take Lx. Lx, for instance, if we take Lx in this case is going to be given as YPZ, like we have here. It is YPZ minus ZPY minus ZPY minus ZPY. So that's what we have on the right side of the equation, and this on this right side of the equation, as we can see, are two components of position and two components of linear momentum. So quantum mechanically, as we always say, all the four quantities are operators, since the product of the two operators is an operator and the difference of the operator is another operator. So we expect the component of this angular momentum to be operator. In other words, what I'm saying quantum mechanically is that I can use a different color. What I'm saying quantum mechanically is that let's take red color. Let's take red color. We say that L, in this case Lx. Lx is nothing but YPZ. YPZ. This is Lx. Minus ZPY minus ZPY. This is our Lx, like you indicated, and our Ly is nothing but ZPY. This is ZPX minus XPZ minus XPZ, and then our LZ in this case is going to be XPY minus ypx minus ypx. So this is what we have. These are the component angular momentum. It is a vector sum of all the components. So the sum of this component, or the sum of we can say this operator is another operator. Angular momentum is an operator itself. We have encountered this type of operator before, and then we can now submit that L is equals to Lx Ly in terms of vector. We can rewrite this in terms of vector, and then we simply cross this. If it is a vector product, let's just take it this way, and then we also do this. So this is what we have in this case. So basically, what I want to clarify in this video is to show you that the component of angular momentum in position space do not commute. It do not commute. It's not like the way we do in mathematics, that if we commute this type of thing, it should have given us a resultant which is 0. But I want to show you that the result cannot be 0. We had this argument, and I would like to clarify it in this video. So let us see whether indeed I want to show that. So I want to show you that indeed these do not commute, and we want to show that the component of angular momentum in position space do not commute. Let's see how that goes. So let's take two components of these two vectors and show that they cannot commute. We want to take the two components of these two vectors. Okay, so let's take two components. In this case, let's take Ly, let's take Lx Ly, Lx Ly. We know that if we are taking these two Lx Ly, and let's say that they are acting on x, the function x, this will mean that this is equal to Lx Ly minus Ly minus Ly Lx. Of course, all this is acting on this function x. But what do we have? We know that our Lx is nothing but negative. This is negative IH cross of this y. Then we are going to take the partial derivative, which is d dz, because remember our Lx Ly, we know what is Lx, it is ypz minus zpy. So it is going to act on this I h cross y d dz plus we are going to have I hz h cross z. This is I h cross z d dy. Of course, this represents this component that you can see here. So this is why we are taking this I h cross z d dz. So this will be, we want to multiply this with I negative IH cross Z, the second one Ly, which is d dy, now d dx, because here we've got zpx, so it is d dx, it is operating on x. This will be plus I h cross now z, I h cross, now this is going to be x instead. This is going to be x, and then v dz, dz. We do the same in the LZ, which is xpy minus ypx. So now we would like to continue to see what we get when we do our differentiation in this form. If we do our differentiation, bringing these two things together, we will have this will be equals to IH cross Y, the way we have it here, IH cross Y, V dz, d dz, plus IH cross Z, d dy, this one was d dz, this is v dy, this now is d dy. So this is what we have now. The whole of this will give us negative IH cross Z, IH cross Z, IH cross Z minus, when we operate on this, we will get negative, because we have negative inside, IH cross Z, IH cross Z, V dx, this is going to be d dx, plus IH x, this is plus IH cross x, IH cross x, d dz, d dz, d dz, just like the way we have it here. And the whole of this is going to give us 0. It's going to give us 0. Therefore, we will end up with negative IH cross, negative IH cross squared. This is what we have, squared y. This is negative IH cross squared y, which is equals to negative h cross squared y, and this is not equal to 0. So I simply want to show you that this computation here cannot be equal to 0. But for more explicit explanation, I have done a part 2 of this video, and in the part 2 I am going to explicitly differentiate this term by term. What I have done is an implicit, this is more of implicit differentiation, partial differentiation, where we have to differentiate them term by term. We have the variable x, y, and z in the same equation, and we have tried to bring them together in our differentiation. But in the second video, which is already there, click on the link below. You will see how we do differentiation so that we get negative I h cross z, and how these have come to 0, to show us that this particular differentiation, or what we have seen here, angular momentum in the space, do not commute. It cannot be equal to 0 like the way we claim during our cross products. Let's continue this video in the second series, where you can learn more in terms of the explicit partial differentiation.